So in this class we discussed the degenerate perturbation theory. In previous classes we have seen the developments or how to proceed with a non-degenerate perturbation theory, and we have also discussed an example for non-degenerate perturbation theory, and that was the Stark effect. So here we consider a system whose unperturbed Hamiltonian H0 is degenerate. So H0 is degenerate. So what does it mean? There exists a set of eigenstates for a given eigenvalue. So we have any given eigenvalue. So it corresponding to that there can be a set of eigenstates. That means more than one eigenstates can have the same eigenvalue for the degenerate states. Whereas in the case of non-degenerate states, each eigenstate will be having, or each eigenvalue will corresponds to one specific eigenstate. Okay. So in this degenerate case, we can write the eigenvalue equation as H psi n is equal to H0 plus HP. As that is, we have split the Hamiltonian into two parts, the contribution from an unperturbed part and the contribution from the perturbed part, like what we did the case of non-degenerate perturbation theory. Then we have psi n. So this is equal to En psi n. So this is our eigenvalue equation. Now the problem is that unlike our previous case, this is degenerate. So that means it can be in general we say that this is f-fold degenerate. F-fold degenerate. So it means that there exists a set of f different eigenstates. So f different eigenstates are possible for each of these En states. Now we distinguish those f different eigenstates as psi n 0 alpha. Okay, this 0 tells you that this is unperturbed, this is for unperturbed energy, and this alpha can be numbers 1 2 3 like up to f. So f different eigenstates are possible for each of these eigenvalue. So that is what we are considering here. So we can write for the unperturbed Hamiltonian H0 psi n alpha 0, the unperturbed state, is equal to En0 psi n alpha 0, where this alpha is given by this thing 1 by 2 etc. up to f. So this is the eigenvalue equation for the unperturbed Hamiltonian, and you can see that these energy eigenvalues En's are independent of this alpha. Now whenever there is a degeneracy, we are free to choose our base set of unperturbed kets. So that means we can choose the linear combination of the degenerate unperturbed ket as the ket of expansion for the eigenstates. What is the advantage of this? We can write the wave function psi n. So that is the wave function of the perturbed state. It can be taken as a linear combination of degenerate unperturbed wave function. That means you can write it as a linear combination of, we have an alpha equal to 1 to f psi n alpha 0 psi n alpha 0 psi n. So this is an identity operator in the unperturbed Ketz, degenerate unperturbed Ketz state. So we are expanding psi n in terms of this eigenkets of the unperturbed state. So this can be written in a simple form. You can write it as sigma alpha equal to 1 to f a alpha psi n alpha 0, right, where this a corresponds to the inner product between these two things. This inner product is basically given by this coefficient a alpha. Okay, so if we make substitution for psi n in this expression, so this is our original equation which we want to solve. So in place of psi n, what we are going to write here is, we write it in terms of this unperturbed eigenstates. So our first equation, something like this one, summation over alpha h0 plus hp a alpha psi n alpha, and on right hand side we have the eigenvalue en summation over alpha a alpha psi n alpha 0. So we have simply substituted for psi n in the first equation. Okay, so this is equal to summation over this alpha a alpha we have here. Now when this h0 acting on this state, what you get is, you get the eigenvalue en0, the eigenvalue en0, then you have psi n alpha 0. So now when this perturbed Hamiltonian act on is hp psi n alpha 0 0, and on right hand side we have en summation over this alpha a alpha psi n alpha 0. Now we multiply both sides with the ket psi n beta 0. Okay, so we get summation over alpha a alpha, then we have en0, then psi n beta 0 psi n alpha 0 plus psi n beta 0 hp psi n alpha 0 equal to, on right hand side we have en summation over alpha psi n beta 0 psi n alpha 0. Now since the degenerate eigenstates are orthonormal, we have these kind of inner products will be a delta function, delta beta alpha. Okay, because those are orthonormal states. So we can write this expression as summation over alpha a alpha en0 delta alpha beta plus we have psi n beta 0. The second time we have to write as that itself, psi n alpha 0 equal to, on right hand side we have En sigma alpha. There is one A alpha term here which I missed out, so you have an A alpha here. So En summation over alpha A alpha delta alpha beta. Okay, right. That means, so we can further simplify it. Out of many A alpha terms possible here, this is a summation over alpha which runs from 1 to f. Only one term will survive, that is when your alpha equal to beta. For all other terms, this delta term will give you, delta function will give you 0. So we don't need to write this summation. The only surviving term will be when alpha equal to beta, that is A beta En 0. So that is the first term, or the surviving term from the first term. And then from the second term we can write sigma alpha from 1 to f A alpha psi n beta 0 HP psi n alpha 0 equal to, and similarly on right hand side the only surviving term out of the summation will be A beta, right? So En A beta. So summation over alpha equal to 1 to f A alpha psi n beta 0 HP psi n alpha 0 is equal to, we take this term to the right side, so we have En minus En 0, then A beta is common, A beta. So this is basically the matrix element HP beta alpha. So this is the matrix element, and En minus En 0. En 0 is the unperturbed energy, and En minus En 0 will give us the first order correction in energy, En 1, right? And also we can write this right hand side of this expression, which is right now En1 A beta, which can be written as summation over alpha En1 A alpha delta alpha beta, right? So this expression will become summation over alpha equal to 1 to f HP beta alpha, the matrix element, minus En1 delta alpha beta into A alpha equal to 0 if you take all these terms to the left side. Okay, so what is this beta? Beta is same as alpha, some index which runs from 1 to f if we have f-fold degeneracy. So what we have seen is that we have seen a system of f homogeneous linear equations for the coefficients A alpha. So these coefficients are non-vanishing only when the determinant of HP beta alpha minus En1 delta alpha beta, only when the determinant of this thing is 0. right? So that means if you explicitly write it out, you can write it as HP11 minus En1. Now the second time will be HP12, the third time will be HP13, etc. Up to you will have F times because of F fold degeneracy. So HP1 of. Similarly, the second one is HP21, then HP22 minus En1, then HP23 up to HP2F. Similarly, we will be having the last term, which is given by HPF1 and then HPF2, HPF3, etc. So this one will be HPFF minus En1, and all these determinant has to be 0. And you can see that this is an fth degree equation in En1. And in general it has f different real roots. So f different real roots are possible. So we can have solutions like En alpha, where alpha can have f different values. So these roots are the first order corrections to the eigenvalue En alpha of the Hamiltonian. To find the coefficients A alpha, we substitute these roots into the equation which we have just seen before. So once we find out these roots, then you can substitute those A alpha, because we will be we substitute those different values for En here, and then we can get the coefficients A alpha from this expression. Okay, so then we solve this resulting expression, and knowing these coefficients, we can determine the eigenfunctions psi n in the zeroth approximation. So how do you get that? You get it from this one. So once you know A alpha, these coefficients, you can find out the eigenstate, the first order eigenstates. Okay, so we have seen how to get the corrections in eigenstates and means the eigen energy eigenvalues. Okay, now the roots En alpha of this determinant are in general different. So in this case, the eigenvalues of the Hamiltonian are not degenerate. Hence, the f-fold degenerate level En0 of the unperturbed problem is split into f different levels. So since this determinant can have different roots, this En alpha can be written as En0 plus En alpha 1. So what I was telling you, these En alpha can have, generally this En alpha can have different values. Different values are possible. See, when you have different values for this one, you can say that this eigenvalue, that this is the eigenvalue in which we have added the eigenvalue of the perturbed system into the eigenvalue of the unperturbed system. So this resultant eigenvalue will in general be non-degenerate. In general, it can be non-degenerate. So in this way, the perturbation actually lift the degeneracy. You can say that perturbation lifts degeneracy, and the lifting of degeneracy may be either total or it can be partial, depending on whether all roots of this determinant are unique or only some of them are different. Okay,